That's not good. Oh, there we go. Okay, chapter 3 is all about graphs. It's the graphical ways of describing data. So this is like the second step really in any study. You're gonna collect the data, and then what do you do with it? First thing that you do with the data is you put it in a graph, and then you're gonna calculate some numeric summaries, and we're gonna do that on Monday. Okay, so different graphs for categorical data. Within bar charts, there's just plain regular bar charts that you guys learned before. There's comparative bar charts, and then there's segmented bar charts. And then pie charts. Pie charts are very, very rarely used. You will never be asked to construct one. You will probably not see it on the AP test at all. But you could see bar charts. They might ask you to interpret them. They might ask you to construct them. Bar charts use either frequency or relative frequency. You get to choose. With the exception of comparative bar charts, when do you have to use relative frequency? What? Sean?
If the sizes of the samples are different.
Different sample sizes, you have to use relative frequency. So a bar chart could be used for one sample or two. A segmented bar chart can be used for one sample or two. Comparative is for more than one, so 2, 3, 4, 5. But if you have different sample sizes, you have to use relative frequency. Here's an example of a comparative bar chart. So you're comparing males and females, guests at a hotel, the number of guests. Okay, anytime that you have a bar chart, these are the most difficult to interpret in my opinion. It's not CSSU and it's not FUDS. To interpret a bar chart, that's where you have to compare the categories to each other. So if you remember, I don't want, this is the most frequent, and then this, and then this, and then this. I want you to compare them to each other. So if I was solely talking about the female distribution, I would say most commonly the female guests were British. Irish and the rest of the world is the next most frequent. It's about 2/3 the frequency of British female guests. And then mainland European is about 1/3 of the rest of the world, and Irish. Do you guys remember talking about this, quantifying the differences? Okay. And then anytime that you have something comparative, like a comparative bar chart, you have 3 things you need to talk about. You need to talk about the female distribution, you need to talk about the male distribution, and then you need to compare them. Again, quantifying. Okay, so I just talked about the female distribution. You would do the same thing for males, and then you would compare them. So between males and females, the number of British passengers or British guests is the most different. There's about twice as many female guests that are British than male. For mainland European, there's the same number of male and female guests. You guys know what I'm talking about? Yeah. Okay. Here's what a segmented bar chart looks like. So a segmented bar chart on your y-axis is going to have relative frequency. They just wrote it as %. Again, you can have one bar chart or you can have a comparative one. So if you just have one, it would be one segmented bar chart. These are all the relative frequencies, so they're always going to add to 100. And then a comparative segmented bar chart, so in this case we're comparing men to women. So same way of describing as you would a comparative bar chart. So you're going to talk about the male distribution, the female distribution, and then compare them. Is that clear? Do I need to compare them again? No. Okay. Pie chart, again, pretty much useless. Really the only time pie charts are used are in newspapers, because that's what everybody knows. But in stats, we don't use pie charts very often. They're difficult to interpret. It's difficult to see the differences between them, and there's no way to make a pie chart comparative. So it can only be for one data set. Okay, that's what we talked about. Okay, this is what I just talked about. I do not want you to say X is most popular, and then Y, and then Z, and then W. I want you to quantify. So the most popular was X. It's more than all the others combined. Something like that. Okay, stem and leaf plots. You guys remember stem and leaf plots? Mm-hmm. Yeah? Okay. This is split stems. So you don't have to use split stems or back-to-back. You guys just remember normal, plain old stem and leaf plots, where you have your stems and your leaves. Split stems is when you split low, high, so low is going to be 0 to 4, high is going to be 5 to 9. And then back-to-back plot looks like this. So it helps you compare two different distributions. Please remember that you need to go in numeric order. The one thing that's confusing about a back-to-back plot is this numeric order on the left is backwards. So it's numeric order starting from the middle. Okay, so a few guidelines with stem and leaf plots. Generally, you only put one digit in the leaf. So you did an example in class in the book that was like 4 digits. So you put 1 in the stem and you put 1 in the leaf, and then you cut off the last 2. Do you remember what that's called? Truncating. Yeah, that's what, I guess I gave you the answer up here. Truncating. It's not rounding. You don't round, you just cut off the digit. If you do put more than one digit in the leaf, you separate with commas. You have to make sure that you give a key. So by a key, there's 2 ways to do this. You could do something like this. 2/1 represents 2.1. Or you could say the stem is the 1's place and the leaf is the 10th place. I don't care which way you do it, but you have to tell the reader how to interpret your graph. Why would I use a split stem? Not back to back.
Oh.
Split.
Like the 2 allowed to combine?
Yeah.
If there's a lot of observations?
Yeah, if there's a lot of observations, sometimes it's difficult to see the center, the shape, etc. Interpreting a stem and leaf plot is CSSU. When do you use CSSU? What types of graphs? Univariate.
Numerical.
Numeric data and univariate, you're going to use CSSU. One thing I don't have up here, for stem and leaf plots, you want between 5 and 15 stems. You really don't want less than 5, you don't want more than 15. If you have less than 5 or more than 15, it's hard to see the center, the shape, the spread, etc. Histograms, these are the ones that we see most often. They use frequency or relative frequency on the y-axis, therefore discrete or continuous. What type of graph is this? Histogram? No. This is a histogram. This is a bar chart. How can you tell that this is a bar chart? Space between the bars. Yeah, bar chart always has space between the bars, and what else? It's categorical data. Yeah, so this is a histogram for a discrete numeric variable. So it's counting something from 0 to 9. So this is discrete. It could be continuous, and they could have put into classes. They could have put their observations into classes. But generally continuous is going to be a curve. So like the normal distribution, when we draw the curve, that's a histogram. It's a continuous histogram. So sometimes you're going to see a histogram like this where each bar represents one specific value. Sometimes you're going to see histograms like this where each bar represents a class. So this class is 140 to 149, 150 to 159. You guys need to be able to construct these. Okay, do you guys remember talking about density?
Yes.
Yeah, what is density? Or when do we use it? Why did we talk about it?
Yes, but that
Not that density. Yeah, if your classes are unequal. So this class, each class is 10 wide, so you don't have to use density. But sometimes you're going to have a data set where the classes are not the same width, in which case you use density. It's relative frequency divided by the class width. And then you put density on the y-axis rather than relative frequency. So this would be a density histogram. The reason that we use density is because your mind doesn't read like the height of the bars, it reads the areas. Thank you. So your mind reacts to the areas of all these bars, not the heights. If you don't use density, then this category, for example, would be really high because it's so wide. Like its relative frequency would be so high because it has a larger width. That's why we use density. Okay, all the shape terms. Skew is where the tail is. And it's called that because the mean is pulled that way. So this is called what? Skewed
Right.
right, or skewed positively, so it's the positive direction, and that's because the mean is pulled towards the tail. So the median is going to be somewhere here, but the mean is pulled towards that tail. So we have right and left, positive and negative. So if you remember, right is positive, like a number line. The normal distribution. When are you allowed to use the term normal? When I tell you that the distribution is normal. Okay, normal is bell-shaped, symmetric. But just because it's bell-shaped and symmetric does not mean that it's a normal curve. Normal curve has a very specific relationship between the mean and the standard deviation. Other shape terms? What else is there? Bimodal. So modal is a peak, so bimodal is two peaks. Unimodal, so one mode, one peak. Multimodal. What else? What terms would you use if you think that the distribution is normal, but I tell you not to use normal? Symmetric. Bell-shaped, thank you. You don't remember any of these? Mound-shaped?
Oh, what?
Do you guys remember heavy-tailed and light-tailed?
Yeah.
So heavy-tailed is exactly what it sounds like. It has longer tails on each side, heavier tails. Light-tailed has light tails. I think that's it. Scatterplots are for bivariate data. You guys should know how to create them. You put X, Y-axis, and then you put points at each of the observations. Scatterplots are the only time that you use FUDs because it's the only bivariate graph. So F stands for form. This is what we talked about like last week, right? Can we just move on? Okay, wonderful. Okay, cumulative relative frequency plots. So this is where you have cumulative relative frequency on the y-axis. So this point, for example, is the relative frequency of 39 and everything below it. So that's how it helps you find the percentile. You might be asked, find the 80th percentile. So in this case, percentile is the percent at or below that value. So I'd go to a cumulative relative frequency of 0.8 and go over, and it looks like the 80th percentile is maybe 75, 72, something like that. I don't really know why this goes above 1. It shouldn't. But cumulative relative frequency is always going to go up to 1. It obviously can't go higher than that. So I don't really know what they did to find this graph. If you have a flat point in a cumulative relative frequency plot, what does that mean?
There's just no frequency of people in that interval.
Yeah, there's nobody in that interval. And the last one is a time series plot. For time series, you're going to have time on your x-axis, so in this case they put year, and then you're going to have some variable on the y-axis. So this is looking at total phosphorus, I guess. But in this case, you're not going to do FUDs because it's not a normal scatter plot. You're just going to look for trends and cycles. So we would say that the total phosphorus is cyclical. It increases, decreases, increases, decreases, increases, decreases. We're going to say the highest peak is in the year 92. After that, there are small peaks in 95 and 98, maybe. We're going to say the lowest point is in, well, I guess 95. But just look for overall trends. Questions? No? We're good? Okay.